continue with this third part and final part of the lectures planned for today. Here are some examples of retaining walls failed after the construction, with the message shown here that although these type of walls are very often constructed in local practice, construction companies are very well trained for building these kind of walls. I really have to mention that it's not uncommon to see the failures like this very large displacement. After that, the total destruction of the walls was performed, and change of this concept of the solution was performed here. Also here, about 100-meter walls totally collapsed after failure. So we still need to follow some main main examples. Some maybe what would be the most useful for you to see is to underline some lessons that are learned after all these failures, and some other that are not shown here. First lecture could be that you should use a quality backfill material. The granular material should be used as a backfill rather than some clay-like material, especially if the height of the wall is over 4, 5, 6 meters. It's really good not to forget drainages, even if during the construction of the wall there is no indication of some underground water. That's not a guarantee that the water will not be there in some 100-year period. How long the wall should be used. If there is no possibility to use drainage, then actually the wall should be calculated in such a way to support this poor pressure in the material behind. It's also not suggested to be very much economical with the reinforcement, because if you do some assumption of the design and if you calculate some reinforcements, you don't have to be. It's not good to try to reduce it as much as possible, because maybe some factor that you assumed is not in accordance with the in situ condition, and that could cause the failure of the wall due to appropriate reinforcement. Of course, the thickness of the wall should always be at least total height divided by 10. That means for 5-meter walls, 15 centimeters in thickness. That means the bottom of the wall here. This should be 50 if total height from the bottom of the wall is 5 meters. It's very important to supervise in situ conditions before the wall construction. Means you should see the conditions at the ground here after the excavation. It's very important to observe it, to check it, and to see if it's in accordance with the assumption that someone or you used it during the design. Some discussion regarding the retaining walls could be to define the advantages and disadvantages of different retaining walls. For example, reinforced earth walls could be very good choice if you want to do some cost reduction and to have some aesthetic aspects of the wall. The construction sequence could be a problem if you use reinforced earth walls and you have a companies that are not very much trained in construction such walls. Definitely that the retaining walls that looks like this, it's a cantilever retaining walls or some gravity type retaining walls that looks like this are the most often constructed walls in local practice. And if you design the wall like this, it's less, it's hard to expect that some mistakes will occur during the construction. But if you do the design the wall like this, then you really need to follow the construction process, and you need to be sure that there is definitely a lack of experience with the construction of the wall like this for the local companies. This was slide that was plan to be like some discussion with you. If you have some experience with retaining walls, anyone who uses geotechnics, it's the most often geotechnical construction. I mean, retaining walls. It's most often used in the civil engineering, geotechnical engineering practice. So if you have some experience with some of these walls and you would like to share the experience with all of us, I would appreciate it. If, if not, we'll proceed to the final part of the today's presentation, and it's a defining some principles and showing you a case study of a viaduct that is founded in the landslide area. So this is the same location as we were before, only few months before. So even this part of construction is not finished. So this is in the rock. You can see the rock here, but the rock ends here. The rock material ends here, and here we are in creeping slope that is moving 2 or 3 centimeters per year down the city of Lens. So this part of the viaduct is constructed, and now the remaining part is to be under construction here in this very specific and problematic area. Here you can see the rock material. So the rock ends here, and the problems starts exactly where the rock ends. This is the layout. So what you see here, this is the constructed part of the viaduct. It ends here. And this part is a part of the structure in landslide area. This is the entrance in the tunnel. We saw this tunnel on the previous slides when we were discussing about observational method design on this example. If you just go 1 kilometer down the hill, you'll get to the regional road and you'll get to this river Bosnia down at the bottom. What you can see on this road is that you always have a repaired road at this place or this place, a few places. This indicates that some sliding occurs even here. And this sliding is really linked with the sliding here that ends around here and goes something like this. If you see this potentially area, you'll see that so many buildings are built here. But remember, this sliding is very slow. The sliding is 1, 2, 3 centimeters per year, and more importantly, is very, very deep. In this area, the sliding is about 16-meter deep, and it's confirmed by the inclinometer measurements. In this area, nobody measured the displacements, but it's probably even deeper. In this area, there's also no information about sliding depth, but there's definitely sliding here. What else can be found? But there are so many uh, shallow depth landslide, like 2, 3, 4 meters, and there are so many cracks on these structures here. When you walk around, you'll see that so many buildings have some cracks on the walls. Also here, you can find some local instability occurring here also. So many local shallow depth instability, but most important for this foundation of the viaduct is actually this deep-seated landslide. So when you look at this cross section, this is this rock part that that is not recognized here in the boreholes at this viaduct, and this is the surface of this very, very slope is around the 10 10 degrees, maybe 11, 12 degrees, very, very almost flat area. But as I said, the most problems with the landslide occurs in the relatively flat slopes. Inclimeter readings in half a year indicated that some sliding occurs in 60 meters, additional sliding at 10 meters, and some surface sliding with a very big, large displacement. Here, the displacements are not that big. It's around 5 millimeters to 10 millimeters. So it's about 1 centimeters in this half a year period. Where this deep sliding occurs, it occurs here, 60 to 70 meters. There is nothing special you can see here. During the drilling process, it is actually recognized at some area with a relatively fast drilling uh, drilling process, it was very fast in this area. Relatively low resistance was recognized here during drilling, so it could be some softer area, of course, indicating that this is a very complex landslide, not the one typical where the topsoil, this is material two, slides on the contact with this relatively solid, with relatively soft rock, but better than this cover soil. So we have a landslide sliding, creeping on a very big depth. That's why the foundation concept was to install the piles that passes to this sliding surface and passes it deep enough to using the following principle. And the principles is we cannot influence this landslide. We cannot stop this landslide. If you look at this picture, there is no way you can stop this so many large area from sliding in the 20 meter deep. So that means we need to design our foundation to 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 resist the sliding that will definitely occur. So it's definitely there's no way that this sliding will not continue to slide, but we need to have strong enough foundation to resist that sliding, and that's exactly what was performed here. So first, the initial conditions were simulated by back analysis, defining the safety factor equal to 1 for this 16-meter deep slope. After that, the well foundation were introduced. The well foundations were, unfortunately, I didn't insert here the pictures uh, of the constructed wells, but the well foundations in the layouts were formed with second piles. So in first phase, the second piles were constructed like this, forming the 8-meter in diameter well foundation. After that, all the material from here was excavated to a depth of about 30 meters. It's a very deep foundation, 30-meter, and then it was reinforced and filled with concrete. So at the end, you have a well foundation that looks like here. Around are piles, and inside is reinforcement with the concrete. So you have a reinforced concrete well that is 8-meter in diameter, that is 30-meter deep, and there is founded about 15 meters in this soft rock. And here you have the sliding that is about 16 meters. So you have 16 and 14. So what happens? You build a well foundation, the sliding will continue. And this is the result of numerical simulation of this problem. Where the sliding occurs, it continues, and it pushes this foundation down the hill. What is important? It is important that the displacements of this well foundation are less than some allowable displacement that could cause some serviceability destruction influence on this bridge viaduct structure. That's why this displacement was controlled to remain under 3 centimeters horizontal displacement. Displacements were calculated to support this sliding force. The sliding force generally can be considered as some passive resistance of this soil behind. So what happened when you have the sliding? It will pass around the piles. The sliding will pass around the piles, but one part of the soil uphill will actually set back on the well foundation. How much is that load? It can be calculated numerically, or it can be analytically defined as 2 to 3 passive passive resistance of this topsoil that is under sliding. Okay, main conclusions of this part of presentation is to have some defined principles of selecting different types. Is that we show you some principles of of different retaining structures. We said we show you the importance of drainage measures, not only for retaining walls made of reinforced earth walls, but also this cantilever retaining walls. And maybe the most important lessons from the case study, not only of the failed walls, but also of the problems like this, is once again is when we are defining the route of some highway section. It's very good option always to not to pass the landslide, not to pass the landslide wherever it is possible, especially a deep landslide, since these structures are very complex. And remember, you need to build 1, 2, 3, 4, 5 around piles, and after that there is the problems start, since you need to excavate all this material and you need to reinforce it and fill it with concrete, and it's really complicated. You need 1 or 2 years to construct this complex structure that looks like this and that will be able to resist the sliding of the soil at the contact with this sliding surface. Okay, do you have some questions? Do I need to explain something else in detail? Do you have some comments? Is there something that should be repeated or more clearly described? Okay, if not, then that's it for today. We'll continue next Tuesday with the fourth parts of this landslide in highway construction lectures. Okay, thank you for being here today, and let's stay in touch next week. Bye.
Thank you. Bye.